Okay, willing participants, here we are. We are in the last unit of the year, which is weird when you say chapter 11, but I do things wildly out of order, so this is where we are at. So, what we're looking at here is intermolecular forces, and this chapter is all about kind of the ease at which things change their state. And also, this is really important when we start talking about the solution process. So, to talk all of this, we need to talk about what are called intermolecular forces. Inter is between things. So, the strengths of intermolecular forces differs. Different substances, different intermolecular forces. These are generally significantly weaker than ionic or covalent bonds. We normally would consider ionic and covalent bonds like intramolecular within kind of a molecule. This is between molecules. And again, what we know is that there's less energy needed to vaporize or evaporate a liquid or to melt a solid or to dissolve a solid than it is to break apart covalent bonds in molecules. They're weaker bonds. But the general rules for bonds still holds. These are just really almost like really weak chemical type bonds, even though I hate to say it that way. So again, it still takes energy to break apart these intermolecular forces. That still exists. Now, another way we can think about this is when something is undergoing a phase change, solid to liquid, liquid to gas, solid to aqueous, whatever, we are breaking or reforming different intermolecular forces. Now, again, lots of properties of liquids depend upon the strength of these intermolecular forces. So boiling point, the lower the intermolecular forces are, the lower the melting and boiling points. In other words, the easier it is to melt or boil something. Less intermolecular force, easier to melt and boil. Likewise, also easier to dissolve. So a great example of this is HCl molecules. HCl molecules have very low intermolecular forces, so that means they boil at a very low temperature. In fact, HCl in its native form is a gas at room temperature. That's how low it boils. So we can see there. So boiling and melting. So a liquid is going to boil when bubbles of its vapor form within the liquid. Now to do this, molecules of the liquid in the liquid stage have to overcome their attractive forces. They have to overcome these intermolecular forces to vaporize. The stronger these intermolecular forces are, the higher the temperature that's needed in which to break apart these intermolecular forces, meaning the higher temperature at which the liquid boils. Exact same principle applies to melting. Now, there are three main types of intermolecular forces and one side category. So in order of decreasing strength from the strongest to the weakest, we're going to talk about each of these independently. There's hydrogen bonding, dipole-dipole, and London dispersion, or just called dispersion forces. Now again, there's one other that's kind of a side one, which is ion dipole force. Real simply, this is just an attraction. So again, ions have a positive or negative charge. Things with a dipole have a positive or negative end. So it's an attraction between polar molecules and ions. Again, primarily in terms of solution formation. And again, these tend to be significantly weaker than covalent or ionic bonds. So, in no particular order, so we're starting in the middle, dipole-dipole forces. So, if I have a neutral polar molecule, so the molecule is polar, this is where, excuse me, the previous chapters come into play. You have to be able to identify, is this molecular polar? If it is polar, that means that one end of the molecule is slightly positive, one end is slightly negative, and positive and negative attract. So that attraction between a positive end of a molecule and the negative end of another molecule, that is the dipole-dipole force. Now generally these only work when the polar molecules are very close together because again these dipole charges, those positive and negative ends, are very weakly positive or negative. So significantly weaker than like ionic bonds, even significantly weaker than the ion dipole forces. So here's kind of an example. So here's a bunch of molecules. We see they're polar. And so we see like positive and negative attraction, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. Again, molecules will naturally align themselves up to kind of increase these, to maximize these positive negative attractions. Think of it almost like having a big bucket of magnets. They're going to stick together. North end and south ends will stick together. These do the exact same thing. Now again, in a liquid, these polar molecules are free to move, and so they will again naturally align themselves. They will naturally configure themselves to create those attractive pieces and to minimize orientations that are repulsive. So we can see here, again, they will naturally align themselves to maximize attraction forces. This is what happens. So again, to have a dipole-dipole force, you have to have a polar molecule. That's the rule. Now, ion dipole forces, again, this is that kind of special category. This exists between an ion, positively or negative charged, and a polar molecule, which has a positive or negative end. The ion dipole forces are going to increase as the charge of the ion goes up, or the magnitude of the dipole moment increases. So again, the more polar the molecule is, stronger the ion dipole forces. The larger the charge on the ion, stronger the ion dipole forces. And this goes back to exactly what we've been talking about for the last couple chapters. And again, here's an example. This is really big in solution formation. So like if I take a sodium chloride crystal, put it in water, sodium and chloride, you have sodium ions, chloride ions, those are ions. Water is polar. So the water molecules you can see here are aligning themselves. Their positive end is attracted towards that chloride ion because it's negative. And this is what kind of facilitates the dissolution of sodium chloride. Whereas here, the negative end of the water molecule aligns itself with respect to the sodium ion because the sodium is positive, positive attracts negative. So again, this is how it dissolves. London dispersion forces, aka dispersion forces. Every molecule experiences dispersion forces. A lot of AP questions will ask you to say, what intermolecular forces are present? If it asks you, what intermolecular forces are present, always list London dispersion forces. Every molecule experiences London dispersion forces. Now, the secret behind this, and it's going to sound super sketchy, but it's why it's the weakest of all of them. So in a molecule, due to just the sheer random dumb motion of electrons, occasionally a temporary dipole exists. In other words, occasionally you're going to end up with more electrons near one end of the molecule and less electrons somewhere else. Wherever temporarily there's more electrons than normal, that part becomes slightly, very slightly positive. Or negative, more electrons, negative, sorry. Whereas where there's slightly less electrons than normal, that would be slightly positive. So it's again creating these very, 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 very slight positive and negative charges. Now they're going to act like a normal dipole, positive and negative attract. But because they are temporary and very weak, this force is very, very weak. It is the weakest of all of the intermolecular forces. So, for example, here is a helium atom. So we can see kind of in frame 1, we have electron near the nucleus, one to the bottom. Frame 2, they're on opposite ends, but frame 3, now you get a place where there's electrons, more electrons in one end than there are another. So in frame 3, that helium atom would be experiencing a very slight dipole because one end has more electrons than the other, and that's why there can be dispersion forces. That's what this talks about. Now, rules for dispersion forces. Again, it's very weak. The first thing we look at in terms of dispersion forces, in terms of strength of dispersion forces, is if two molecules have roughly the same number of electrons and shape. Their dispersion forces should be equal. So this is now telling us the two factors, number of electrons and shape. That's what determines the amount of dispersion force. Now, when the molecules of two different substances differ in number of electrons, now we can talk dispersion forces. Now there's a difference. And generally, more electrons means stronger dispersion forces. And as a note, the quick way to do this, I want to be very clear, we have to be careful about it, is that generally more massive molecules means more electrons. But specifically, if an AP question says, why does this molecule have greater dispersion forces, do not say it has more mass. No, 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 no. It's not because it has more mass, it's because it has more electrons. The mass is just a quick and dirty way to see that. So that's what you really need to know there. Now, before I move on to hydrogen bonding, real quick, assume that dispersion forces will be the weakest. Assume that. Now, there are cases where dispersion forces can actually be significant and will lead to greater intermolecular forces than even like polar molecules. Never assume that. Always assume that dispersion forces are going to be the weakest. But if you're told that a molecule has greater intermolecular forces and all it has is dispersion forces, then chances are you can go, oh, there's more electrons in that and the dispersion forces are just abnormally high. So that's kind of how you have to approach that. Finally, hydrogen bonding. This is the strongest of the three. It's really a special case of a dipole-dipole interaction. Now, to have this, you have to meet some very specific criteria. It has to be between the hydrogen atom and a polar bond, and it's going to be the attraction between that hydrogen atom and a polar bond and an unshared electron pair on a nearby small electronegative atom or ion. Basically, what we need to see is hydrogen-fluorine bonds, hydrogen-oxygen bonds, or hydrogen-nitrogen bonds. That's what we need. Now, it's not the attraction between the hydrogen and the fluorine, it's the attraction between the hydrogen as part of each of those and the electron pair on another molecule, and I'll show that in a picture coming up. So again, it's going to be that the attraction of that hydrogen to the electrons on a fluorine, oxygen, or nitrogen on another molecule. So for example, HF is a great example. There's hydrogen bonding on it. And so what we see here is we have two hydrogen fluoride molecules, and the dotted line represents the hydrogen bond. So the attraction is between the hydrogen and these electrons on the other molecule. And again, it's really just a unique, very strong form of a dipole-dipole attraction. Because fluorine, nitrogen, and oxygen are so electronegative, those bonds are very polar. In fact, it's so polar, the hydrogen is almost a bare proton. Because if the electrons are almost completely removed from that hydrogen, a hydrogen atom with no electrons is just a proton. So you have this kind of naked proton sitting there almost. And so it's going to be strongly attracted to electrons on another atom. So again, very large dipole effect, but again, has very strict requirements. You need to have that hydrogen attached to a nitrogen, oxygen, or fluorine, and it's going to be attracted to the electrons on another oxygen, nitrogen, or fluorine. So here's an example, water. Water is a great example of a hydrogen bonding. So we see this hydrogen here, which is attached to oxygen. And if I look at the Lewis structure of water, we'd have those two lone pairs. So it's the attraction between this hydrogen and those lone electrons, that lone pair on that oxygen. That's the requirement. So again, with increasing strength comes increasing requirements. every molecule experiences dispersion forces. Polar molecules will experience dipole-dipole. Polar molecules, where there is a hydrogen attached to a nitrogen, oxygen, or fluorine, can experience hydrogen bonding. Again, still weaker than a normal ionic or covalent bond, but it's stronger than dipole and stronger than dispersion. Now again, and I'm stressing this, the hydrogen is required to be attached to the oxygen, nitrogen, or fluorine. So a great example of this, here's two molecules. We have ethanol and dimethyl ether. Their chemical formulas are exactly the same. The only difference, that red thing, is the oxygen, where that oxygen is. And so in this case, the carbons would be black, oxygen would be red, hydrogens would be white. They have the exact same molar mass, exact same amount of electrons, but we can see here the ethanol has a substantially higher boiling point. That means stronger intermolecular forces. Well, why is that? Well, in ethanol, you have hydrogen bonding because there's an oxygen, there's the hydrogen. So that hydrogen can be attracted to the electrons on the oxygen of another molecule. Whereas with the dimethyl ether, there is no hydrogen attached to that oxygen. The hydrogens are all attached to carbons. So there is no hydrogen bonding. In fact, it might be polar. It might have some dipole-dipole interactions. I'd have to draw the structure to be sure. But there's definitely no hydrogen bonding. And that's why we see that huge difference in boiling point and melting point. Now again, comparing intermolecular forces, so every molecule experiences dispersion forces, and bad, Ms. Anderson, not molecular weight, number of electrons. Shame on me, I do not get to pet a cat today due to that level of shame. So more electrons, more dispersion forces. Also, longer molecules tends to give greater dispersion forces. Basically, the more wiggle room there is, the more options there are for those tiny little dipoles to be created, bigger the dispersion forces can get. Then we get to dipole-dipole. Again, every molecule that has dipole-dipole has to be polar. Every polar molecule still experiences dispersion forces, but dipole-dipole gets added on top of that. But again, has to be polar. And finally, hydrogen bonds requires not only a polar bond, but specifically a polar bond of a hydrogen attached to fluorine, oxygen, or nitrogen. Now again, you can assume things with hydrogen bonds will have the greatest intermolecular forces, dipole-dipole will be in the middle, dispersion forces only, bare bottom. But if you are told that a molecule that isn't polar, so that means dispersion forces only, is something that is non-polar, has a higher boiling point or a higher melting point than something that is polar, that's telling us that those dispersion forces are really large. In fact, they can be larger than dipole-dipole interactions, and that's usually due to a very large number of electrons. Now again, you would never have to guess that, but you are expected to be able to explain that. Okay, so now that we have the basics of intermolecular forces, we can start doing some just selected topics, just applications of it. So one application is this idea of vapor pressure. So anytime we have a liquid, technically even anytime we have a solid, but really we focus on liquids. If you have a liquid, due to the sheer random dumb luck, occasionally a molecule here, a molecule there gets enough energy to go from liquid to gas phase and to evaporate. Now, imagine that we take something like ethanol and we put it into a evacuated, that means nothing else is in it, it's sealed container. The ethanol will begin to evaporate just at room temperature. And so that means as it goes from a liquid to a gas, the pressure in there goes up because there's now vapor. There's gas. So pressure goes up. Vapor pressure, by the way, is the pressure of that vapor. Eventually, the pressure of the vapor will become a constant value. That's called the vapor pressure. So when left alone in a sealed container, that's the pressure that a liquid's gaseous phase will produce. Now we can see here water, liquid water. Most liquid water is liquid, but a few molecules do happen to get enough energy to turn into a gas. Because they're now a gas, they can create pressure, and we call that vapor pressure. Now explaining this, so again, molecules within a liquid, as we know, move at various speeds. So at any given instant, some of the molecules at the surface of the liquid will get enough kinetic energy to overcome the intermolecular forces tying it to its neighbors, thus going from a liquid to a gas. Now the weaker those intermolecular forces are, the more particles that can escape, and therefore more vapor pressure. So what that's telling us is lower intermolecular forces means higher vapor pressure. Now, at any given temperature, the movement of molecules from liquid to gas goes on continuously. And as the number of gas molecules increases, the probability increases that a molecule in the gas phase will hit a liquid surface and be recaptured. So again, as we let things sit, occasionally the gaseous molecules will actually re-hit due to sheer random motion, re-hit that liquid. They will give some of their energy to the molecules in the liquid, so they lose energy, and then they're recaptured and they're a liquid again. So eventually you reach this dynamic equilibrium piece. The rate at which the molecules return equals the rate at which they escape. And so you end up with a steady, constant number of molecules in the gas phase, which leads to a steady pressure. And again, we know dynamic equilibriums. I'm not going to preach that over much. So the liquid and the vapor are going to be in equilibrium when evaporation and condensation occurs at equal rates. This will often appear like nothing's happening, but there's no net change going on. But again, the molecules are constantly shifting from liquid to gas, gas to liquid. And again, vapor pressure is just the pressure of the vapor once we reach equilibrium. And we can see that here. So here we start all liquids, some start evaporating. Now some are evaporating in, some are condensing back down, and eventually we hit this equilibrium piece in the middle. Now, substances with a high vapor pressure, if we think about this, to have a high vapor pressure, that means that more molecules will be in the gas phase. More molecules were able to escape being a liquid. Now again, to escape being a liquid, you have to overcome the intermolecular forces. So, we call liquids that evaporate easily, we call liquids that have a high vapor pressure a volatile liquid. And as temperature increases, the particles increase, they're moving around more, and that means more will evaporate, that means vapor pressure increases. So vapor pressure does go up as temperature increases. Now, a liquid boils when its vapor pressure equals atmospheric pressure. So this is kind of interesting. So we talk about that water boils at 100 degrees Celsius. Well, why is that? Well, it turns out at 100 degrees Celsius, again, higher temperature means higher vapor pressure. At 100 degrees Celsius, at 1 atmosphere pressure, or 100 degrees Celsius, the vapor pressure of water equals 1 atmosphere. So when vapor pressure equals atmospheric pressure, then it boils. Now, that means higher boiling points. If something has a higher boiling point, that means you need a higher temperature to reach that. So if something has a higher boiling point than water, that means you need a higher temperature to reach that same vapor pressure. Now again, higher vapor pressure means lower intermolecular forces. So if something has a higher boiling point, that's telling us that it has stronger intermolecular forces. Okay, last little bit. So again, we're skipping to chapter 12. We talked solution chemistry start of the year. We're coming back to this. So, any type of intermolecular force can operate between solute and solvent in a solution. So that means, again, you can have just dispersion forces holding a solution together. You can have dipole-dipole. You can have hydrogen bonding. You can have that ion dipole. But there's 3 interactions we have to consider to determine if something will dissolve. First, solute to solute. So solute, like let's say you're trying to dissolve something in water. So you have to overcome the solute to solute attraction, solute to solute intermolecular force. The greater that force is, the harder this is for something to dissolve. Water, as weird as it is to talk about water being this universal solvent, actually has hydrogen bonding. So pretty strong attractions between the solute. So we have to put energy in to break apart those intermolecular forces between the solvent particles. Then solvent, or solute, so yeah, I think I said the same thing. So again, now we're talking solvent. So solute, everything I said with solvent applies, same thing. We have to break apart the solvent and the solute particles in order for something to dissolve. Finally, solvent-solute. There has to be an intermolecular attraction between the solute and solvent. And because we're now attracting things, that's exothermic. Now, how much something dissolves will depend on the relative strength of these three interactions. Solutions will form when the solvent-solute strength is about the same or greater than the solute-solute and solvent-solvent force, or attraction. So if we see things that, let's say, don't dissolve in water, the reason they don't dissolve in water could be twofold. One, the attraction between the solute and solvent is weaker than the solute-solute or the solvent-solvent. Whereas when something does dissolve in water, that tells us that the solvent-solute attractive force is greater than those two. That is what is required for something to dissolve. Now, to do this, you have to analyze the types of intermolecular forces present. And that's what we see here. You can pause if you want. So let's look at sodium chloride. Sodium chloride is going to dissolve in water because the solvent-solute interaction between polar water and ion. So it's a dipole ion interaction. That attractive force is similar to the solute-solute, so that's the sodium chloride ion attraction to each other, and it's similar to the solvent-solvent, the polar water molecules to each other attractions. Because they're similar, it'll dissolve. So again, it has to be greater or similar to both the solute-solute and solvent-solvent. Now, an overview in general, the stronger the attractions between the solute and solvent, the greater the solubility will be. What that means is, in general, a polar solvent will be able to dissolve ionic or polar solutes because, again, there's more attraction. Polar solvents will not be able to dissolve a nonpolar solute because the nonpolar solute doesn't have that great of attractive force to the solvent than the solvent has to itself. The solute-solvent attractive force is not enough. Likewise, if I have a nonpolar solvent, if I have a nonpolar solvent and I put a polar or ionic solute in, it's not going to dissolve. Because then the attraction between the solute and solute is going to be greater than the attraction between solute and solvent. Now, solubility and pressure, real quick. The solubility of a gas increases as pressure goes up. That's just what happens. Temperature, solubility of most solids increases, temperature goes up. Gases are going to go backwards with this, and that's because you're giving those gases enough energy to escape and just run free.